Good afternoon, ladies and gentlemen. My name is Pavel Pokorný, and the title of my presentation is New View on Crack Closure Determination from Compliance Data. Here you can see the graph, experimental results of the crack propagation rate versus stress intensity factor range. It is for Ravel Exo Steel EA40, and the results are obtained for various load ratios. However, if you have a look to particular delta K, particular stress intensity factor range, you will have the different crack propagation rates due to the load history, due to the different load ratios, etc. But actually, we would like to have some unique parameter which describe uniquely the crack propagation rate. So this unique parameter could be effective value of stress intensity factor range, where we take into account just the part of the load cycle when the crack is open. So then the delta K effective means that we took the maximum stress intensity factor minus K closure. But the problem is that it's not easy to determine K closure. We have some attempts, how can we determine it? The first kind of attempts is we can calculate it somehow. We can use, for example, some strip yield model, which is, for example, implemented in FastRun code, which is a well-respected code for modeling of plasticity-induced crack closure. We can use the finite element method for assessment of the crack closure, or we can determine the crack closure by the experiments. And here are our data on the left, and I kindly ask to Professor Newman from Mississippi State University, who developed the so-called FastRun code, which is, as I said, quite a respected code for evaluation of crack closure. And Professor Newman provided this data, as you can see here on the right, when we have a crack propagation rate independence of effective value of stress intensity factor range. However, we want that one single curve, which all data measured at the various load ratios should collapse into one simple curve. But actually, as you can see here in the threshold area, this is not true, and we have here scatter. And this scatter is caused due to the fact that the fast run just cover plasticity-induced crack closure. But in reality, we have the presence of the other sources of the induced crack closure as the roughness and as the oxide. And as you can see in this graph, the roughness and oxide-induced crack closure are significant in the threshold area. The clue that oxide-induced crack closure is present in our Ravel Exo EA40 is that we can generally observe some oxide debris at the surfaces of our specimen. Due to the fact that so far we cannot model oxide debris and oxide-induced crack closure, there is just one simple way how we can obtain that, and we have to measure it experimentally. However, nowadays we are still working on some model which can calculate the effect of oxide-induced crack closure, but still it's ongoing process. The first way how we can expect the crack closure level is when we have some experimental data which are determined on very high load ratio, as for example 0.8, when such a high load ratio means that there is not crack closure at all. And when we have some data which are determined on some crack closure load ratio, e.g. -1, so then if you know this known formula and you express crack closure, then you can determine crack closure from this formula, because it's just the difference between the key max and the delta K effective. So the difference between these two curves should be crack closure. The second way how we can determine crack closure is from the compliance data, which means that we have some record of the load versus strain or displacement Uh, uh, so when we have the specimen with the crack, we have different stiffness when the crack is opened and different stiffness when crack is closed. It's also necessary to say that compliance is the inverse function of the stiffness. When we use the derivative form of this record, we will obtain some compliance offset record, as you can see here. You will obtain somehow the data which are in the black curve, as you can see here. It includes some noise. So then you have to somehow smooth the data to work with this data. And due to the fact that crack is not closing and opening very sharply, but it's continuous process. So then we have some criterion given by the ASTM, for example, 1, 2, or 4% of change of the original offset, which is for the fully opened crack, for the specimen with the fully opened crack. Here, I would like to show you some experimental results obtained on middle tension specimens when we glued strain gauge over the central notch and we investigated the compliance data. Here you can see two graphs, which are just the representative graphs. The same experiments were carried out on another approximately 70 specimens. And you can see here that in the case of compliance data, when we have a force versus compliance offset according to ASTM, then the expected crack closure, which is given by this formula, is approximately very similar to the crack closure determined by according to ASTM criterion 4%. Here you can see the results for approximately 17 points, which were obtained at the various load ratio, and we calculated according to compliance data, according to ASTM, into the delta K effective, and you can see that simply it seems that it works in this way. However, determination of crack closure in this way is not effective, because imagine when I glue the strain gauge in the central notch, this strain gauge will survive just one or several load cycles. So it means that for measurement of one crack closure level, 1 point, I need one strain gauge, sorry. So for measurement of 20 points, I need 20 strain gauges. So, and you can see that this is not effective way how we can determine the crack closure. So then we tried to measure the crack closure at CT specimens. According to this paper, which was written by Yamada and Professor Newman, we tried to measure crack closure by using of 3 strain gauges, which were glued close to the path of crack growth. And here you can see that in the case of the strain gauges, first strain gauge was in the position 8 millimeters, second one 70 millimeters, and third one for 25 millimeters away from the notch tip. Also, we tried to measure crack closure by the crack mode opening displacement gauge, which was the clip on from the front side of the specimen. Here you can see just one representative case. When we measured the crack closure, it was for CT specimen when we had a crack length approximately 50 millimeters long. Here you can see the rest parameters during this experiment, and from the crack growth rate, we could calculate the crack closure expected. But here you can see the data which were obtained. The first column, first data corresponding to the crack mode opening displacement gauge. The second column corresponds to the strain gauge 1, then to the strain gauge 2 and strain gauge 3. The dashed violet line should be expected level of crack closure according to previously shown formula. And if we have a look from the point of view of the ASTM standard, which represents to the green points, you can see if we start with the strain gauges results, that if you have a look to the data from the strain gauges, you see that this data includes such a huge noise And also for a case of string gauge 1, there's a multi-cross of some limit given by the ASTM. So it's questionable if the data from the string gauges could be used. And again, if you have a look to the data of the string gauge 1, it seems that according to ASTM, the crack closure is underestimated, but in the case of the string gauge 2, it seems that it's overestimated, but still it's questionable because the signal coming from the string gauges is quite poor. In the case of the string gauge 3, there is a very pure signal because there is a combination of the bending and tension load. So the signal is very weak, and I think that's useless to use this data for evaluation of crack closure. If we have a look to the crack mode opening displacement gauge data, if we used the standard ESTM criterion for %, you will see that according to expected level of crack closure, the crack closure is underestimated. But if we have a look from the new view to this compliance data, that we could have also present another source of nonlinearity except of crack closure. There could be just the simply different source of nonlinearity. And if you have a look that there is a rapid change of the slope, and we assume that the crack closure appears here, so then this expected value is much closer to the crack closure as we expect. There is a second case of this experiment. It's the same setup, but we have another crack length of 27 millimeters and different crack grow rate. So then we can also expect some value of crack closure. And what is the necessary? That in this case, the crack already passed the strain gauge 1, and the crack is in the middle position of the strain gauge 2. So in this case, when the crack tip is behind the strain gauge 1, then the data coming from the strain gauge 1 are useless anymore because you can't use this source of data for a long time. So then, if you have a look to the strain gauge 2 results and strain gauge 3, it seems that, again, there is a quite huge noise, and it seems that if we somehow smooth the data, that in the case of the notch 2, the data according to ASTM are all underestimated of crack closure, and in the strain gauge 2, strain gauge 3, the data of crack closure are overestimated. When we look to the crack mode opening displacement gauge, and according to ASTM standard, it's again underestimated. But if we take into account that there is another source of nonlinearity except of crack closure, and we assume the crack closure is here where is the breakage point of the compliance data, then this point is much close to expected level of crack closure. So please let me conclude my talk. The current models of crack closure, like faster or finite element modeling, considers just crack closure due to the plasticity. We work on modeling of oxide-induced crack closure, but still it's an ongoing process. So nowadays, we cannot calculate the total crack closure. Therefore, we have to measure it by experiments. For measurement of crack closure, there is not simply approach, and it seems that the ASTM criterion does not work in the case when we use the crack mode opening displacement gauge data. The crack closure measurement by CMOD gauge provided better results of crack closure compared to local strain gauges. To this last point, I would be grateful if there is anybody else present in the audience who has the experience with the measurement of crack closure that we could discuss and exchange our experience. Thank you for your kind attention.